I'm going to play a video that runs about 5 minutes, and then right after that, we'll begin the webinar.
One of the most exciting things we've seen is putting our system on a shake table and watching it move and understanding after the dust settles, so to speak, that it's in the same place, it's functioning, it's still operating, and it can take the toughest earthquakes that nature's going to dish out. My name is Mike Williams. I'm the Senior Vice President of Engineering for SunLink. SunLink is a ballasted system provider based in San Rafael, California. It initially had a terrific concept about linked solar array racking systems, hence the name SunLink. However, the last couple of years, we've expanded our product offerings. We now have combiner boxes, wire management, and extensive engineering support. So we're a full-service balance of system provider. Over the last 7 years, SunLink has invested well over $2 million in research and development. We do this to continually improve our products, to demonstrate that we can provide safer, more cost-effective, and efficient systems for our customers. One of the strengths of the SunLink R&D program is our relationship with other firms and entities. Rutherford & Jacquin is one of the premier structural engineering firms in the country. We've been fortunate to solicit their help and input on various algorithms for analyzing our systems, as well as interpreting the data that we collect during our field trials.
Rutherford & Jacquin has been in partnership with SunLink since 2008. We provide structural engineering services in support of SunLink's product development and product design. We also support them in installation of their products and various rooftops throughout the world. Some of those rooftops are in high seismic zones, and we have to answer the question, what will happen to a solar array when a large earthquake strikes? I'm Joe Maffei. I'm a structural engineer and a principal with the firm Rutherford & Jacquin, a structural engineering firm in San Francisco. SunLink asked Rutherford & Jacquin if we could demonstrate the acceptability of solar panel installations on roofs without any positive attachments to the structures. That's solar panel installations held down by the weight of ballast only. And to solve this problem, Rutherford & Jacquin created computer analysis models of the possibility of earthquakes striking a building that has a solar array on top. We're able to model this in simulation on the computer, considering a range of possible earthquakes, a range of possible building types with different dynamic characteristics under earthquake motion, and determine how much the array would move. We felt very confident in our analyses, but we said at the time, boy, it sure would be nice to be able to put this on a shake table and verify our analyses with an experiment.
We were fortunate to be able to take advantage of our relationship with the University of California in Berkeley. They have and operate one of the largest shake tables in the U.S. Over the last 2 weeks, we've had a team of people here putting our systems on the shake table. These full-scale production systems show us exactly how our systems respond to various seismic events.
We wanted this test to be as realistic as possible, and we ran a total of 119 unique combinations of solar array type, roof slope, roof properties, and earthquake motion. This test includes 60 instruments on the roof, accelerometers to measure the acceleration of the roof surface itself and the acceleration of the array itself on top of the roof. It includes potentiometers and displacement transducers to very precisely measure how far the array moves with respect to the roof.
One of the things that we found in the test is the whole idea of a linked system works really well. The systems behaved well, remained intact, continued to function, and came through the seismic testing 100%. SunLink finds that the interpretation of the data from the field test really helps permitting officials understand the performance of our products on roofs. This typically enables our customers to have a shorter and more efficient permitting process. This R&D effort was funded through the California Solar Initiative. SunLink was awarded a grant, which was designed to help reduce the cost of solar installation in California and to increase the size of the market. As with all of our testing programs, the results, the things that we learn, feed directly into our product development cycles. We use the information that we gain from these tests to improve our products, to make them more cost-effective, more efficient,
is unique in the solar industry for its commitment to research and development, for its willingness to invest in technology, to invest in gaining new knowledge. Eventually, the entire industry will benefit from SunLink's research.
Thanks everyone for joining us here today for Designing for Earthquakes, Lessons from SunLink's Full-Scale Shaking Table Experiments. My name is Rob Ward. I'm part of SunLink's structural engineering team. I'm here today with my colleague Kate Miller, and we're excited to tell you about our recent shaking table experiments and what the results mean for rooftop array design and for the solar industry. As we move through the presentation, please feel free to submit any questions using the chat feature. We'll be fielding questions as appropriate both during the webinar and at the end, and we'll follow up afterward with anything we weren't able to address right away. Here's the agenda for today's webinar. I'll talk briefly about unattached solar arrays and current code seismic design options. Then Kate will take over and present SunLink's Seismic R&D program and our findings. And after that, I'll go over what this work means for the solar industry and for code development. Then we'll wrap it up and answer questions. Unattached PV solar arrays are PV arrays on flat or low-slope roofs that do not attach to the roof structure. Instead, they rely on weight, often with additional ballast, and friction to resist wind loads. Arrays that are attached to the building will typically require numerous roofing penetrations. Each attachment is expensive to install and to flash. They increase the risk of roof leaks, and they will probably require periodic inspection and maintenance. So we found that installers and building owners tend to prefer unattached rooftop systems. They offer significant advantages from both a cost and a roof integrity standpoint. There are no roofing penetrations, no expensive flashing details, they're easier to install, and there's reduced maintenance. But there's a challenge in high seismic zones. How is it possible to design unattached systems to meet code life safety performance? I'd like to quickly remind everyone where high seismic zones occur in the U.S. In code speak, high seismic zones are typically seismic design category D and above, which on this is a 2% and 50-year peak ground acceleration map, would typically occur in kind of the magenta down through some of the yellow areas. That's primarily the West Coast, Alaska over there in the Atlantic Ocean for some reason, Hawaii, Sierra Nevada, and parts of the Rockies, New Madrid, and South Carolina. In the U.S., seismic design requirements are based on standard ASCE 7, minimum design loads for buildings and other structures. Chapter 13 of ASCE 7 addresses building equipment in high seismic zones, and section 13.4, not sure if it's legible, requires that equipment be positively attached without considering friction that's caused by gravity when designs are based on calculations. But there are some other design options that are mentioned in the codes. Section 104.11 of the International Building Code, which is the model for most U.S. building codes, allows for the acceptance of alternate methods where it can be shown that the intent of the code in terms of life safety and performance is met. Also going back to ASCE 7, section 13.2, it allows for seismic qualification of building equipment through analysis. testing, if it's based on nationally recognized standards such as AC 156, or the use of experience data, again, if it's based on nationally recognized procedures. So this is basically the genesis of SunLink's R&D program on unattached arrays. We wanted to know if it would be possible to use testing and/or analysis to understand, characterize, and quantify the behavior of these systems during large earthquakes. And if that were possible, would it also be possible to arrive at a design approach for these systems that meets the design intent of the building codes? Now I'd like to turn things over to Kate, who will present SunLink's Seismic R&D program, including the shaking table experiments.
Thanks, Rob. I should start by saying that SunLink's Seismic R&D program is funded in part by a matching grant from the California Solar Initiative. The goals of the CSI grant are aligned with SunLink's goals of expanding the solar industry and increasing the percentage of energy we derive from solar fields. Additionally, the lessons we learn in seismically active California have broader implications for the nation and worldwide as we strive to grow the rooftop solar market. Also, if you saw the seismic video that we showed before we started our presentation today, we've worked very closely with Rutherford and Chikeen on all of our R&D programs, particularly the seismic program. When we first began looking at the challenge of putting ballast-only, unattached arrays on roofs, we built analysis models to better understand how our arrays might move. These analysis models accurately capture the primary parameters that affect the behavior of solar arrays, such as a range of possible SDS values, variable friction coefficients depending on the interface between the roof and the PV system, and the slope of the roof. After creating our models, we ran them with a set of roof motions that we were able to summarize the predicted array displacements in a design table based on the results of those analyses. This design table provides the engineer with a method to account for the specific conditions on the roof and come up with a displacement value, thereby simplifying the engineering process for each specific project. And as you can see in this image, it's a close-up of one of our roof systems, and the friction between the recycled rubber foot and the roof, as well as the friction between the ballast pan and the roof, are going to have a significant impact on the results of our analysis models. So each of these interaction surfaces was assigned a different coefficient of friction in the model in order to accurately capture the behavior of the system as a whole. The friction values assigned to the interfaces between the roofs and SunLink systems were determined from full-scale pull tests on different types of roof membranes, which you can see in the lower left images. PVC, MCS, TPO, and EPDM membranes were tested, both in their wet and dry conditions, in order to determine a conservative range of COS values. Additionally, our analysis models were created as lumped mass models, which conservatively ignored the internal damping of the array structure. And we looked at seismic intensity levels from SDS of 0.25G to 1.5G, as well as both uniform and non-uniform roof slopes between 0 and 7 degrees. In order to come up with the roof motions we used for our analysis models, we used the California Strong Motion Instrumentation Program to select 7 roof motions. These roof motions encompass different earthquakes, geographical locations, soil conditions, and building types in order to get a good sense of how solar arrays will move in a wide variety of earthquake scenarios. The recorded motions were all scaled to an SDS value of 1, which you can see in this figure. Important to note is that the constant acceleration and constant velocity portions of the response spectrum are essential in accurately predicting the overall displacement of the array. Since an initial high acceleration is required to induce sliding, but the final amount of sliding, or final array displacement, is related to the relative velocity, as sliding will continue until the velocity of the system goes to 0. In this figure, you can see that the scaled motion in green fits very well with the target motion, which is in blue, and it's conservative compared to the recorded motion, which is shown in red, both in the constant acceleration and constant velocity portions of the spectrum. After creating and analyzing our computer models and finalizing our design tables, we were very interested in pursuing actual shake table tests in order to validate our work. In order to meet that objective, we developed a test matrix that encapsulates the same common unattached PV designs and key variables as our analysis models, and we ran a suite of 7 earthquake roof motions ranging from everyday tremors to the 1,000-year event. Our testing took place at the UC Berkeley Pacific Earthquake Engineering Research Center shaking table, which is the largest multi-directional shaking table in the United States. The systems were tested on 2 18 by 25 foot timber framed roofs, one with a polyvinyl chloride or PVC roof surface and the other with mineral cap sheet or MCS roof surface. And as you can see in the images here, we put the timber roof frames onto a steel frame, and then we fed the shake table our roof motions directly so that the frames were themselves seeing what a roof would see in a normal building. We measured displacements at 6 locations on our PV arrays and measured accelerations at both the feet of the array and at the panel level so we could really get a complete picture of what our array was doing. And this is our test matrix, which summarizes both the breadth of tests and the kind of completeness of design that we were trying to test. So we used the 2 roof membranes, 2 roof inclines, both 0 and 4%, wet and dry surfaces, both SunLink PV roof systems, core and precision, and 2 different ballast weights, a heavy and a light system. And now I'd like to show you a video to get a glimpse of the type of testing that the systems were subjected to. So this is the lab where we did our tests, and that's the core system that you see on the roof at the moment. And this is one of our shake table tests. In the smaller earthquakes, the 0.5 SDS, our system didn't move at all. And then in the larger earthquakes, it moved just a few inches on a flat roof and a little bit more when it was put on an incline. Here you can get an idea of the type of data that we gathered. This slide shows the displacement orbits at each data collection point on a SunLink system. So you can see that we collected data at each of the 4 corners of the feet, and then we also had displacement. We were gathering displacement data at the middle of each array. The orbits are similar in shape and the total displacement values, confirming that our rooftop arrays move as single rigid bodies. We also created planar analysis models in order to directly compare our analysis results with our measured results from the shake table. I'm going to show you a short video of that analysis. And this is the same system as was shown in the real test. So this is our core system, and this is a light ballast configuration. So there's no ballast in the center panel, which is why you see more fluttering of the modules themselves. And again, the system moves just a few inches in the X and Y directions. So the results of these tests of our analysis and our full-scale shake table test allowed for the verification and calibration of the computer analysis models. Our ability to accurately predict displacements of the system, verified by these graphs showing a good match between the test data, which is the shake table test shown in red, and then the analysis, which is shown in blue, confirms our ability to safely put unattached solar on rooftops in seismic regions. And now a bit to summarize just our findings from both our analysis and our full-scale tests. For systems on low-slope roofs, designers can accommodate seismic displacement demands by providing adequate spacing between solar arrays and the roof edge or other fixed objects, and by providing adequate displacement capacity for electrical wiring. So I think the main point that we're really trying to get at is that our analysis can in fact accurately predict the displacements of our solar arrays, and then we can accommodate for those displacements in the system design. And also, shake table tests and analyses both clearly demonstrate that friction at the roof surface limits the sliding displacement that solar arrays experience when subjected to earthquakes. Analytically developed design tables provide conservative sliding displacement demands, which really confirms the analysis ability that we have to include friction in our models. I should also add that from a SunLink product perspective, both the core and precision roof mount systems prove themselves capable of withstanding approximately 100 earthquakes each, ranging in intensity from the SDS values of 0.5, or the sort of tremors that everyone in California feels regularly, to the 1,000-year event, or the SDS value 1.5. And not only did our systems themselves come through the seismic tests really well, but so did the roof surfaces. A certified and licensed California roof inspector evaluated the condition of the roof surfaces post-testing and found that the extensive interactions between the SunLink roof mount systems, which are primarily on rubber feet, and the roof membranes themselves did not cause any damage or compromise the integrity of the roof membranes in any way. And for those that are interested, that full roof inspection report is available on SunLink's website. Now I'd like to pass back to Rob so he can go over some of the industry implications and the proposed seismic requirements.
And thanks, Kate. Well, first I'd like to mention two recent papers describing SunLink's seismic R&D work. If anyone's interested, this would provide some additional information beyond today's presentation. First, there's SunLink's report submitted to the California Solar Initiative Research Program on our shake table experiments. Second, Kate, just earlier this month, Kate, together with RNC, presented a paper at the Joint California-New Mexico Structural Engineers Convention. I titled this slide, Upcoming Additional Information. I believe these documents will be available very soon at the websites I've listed here, but when I checked this morning, we're still not posted. You can contact SunLink if you're interested as well. Skipped over this slide. When I introduced Kate's portion of the talk, I put the question up that got us started on the seismic R&D research effort. Is it possible to use testing and analysis to meet code requirements for unattached arrays? So together with RNC, the answer we found, as Kate has said, is yes. We're able to characterize expected seismic displacements based on tested friction coefficients, roof slope, and seismicity, and then we can design for it. There's a new document out. This one is actually available that I think is quite valuable. Last month, SEOC, the Structural Engineers Association of California, published a technical report on seismic requirements for rooftop solar arrays. It's currently available, I think it's $20 at seaoc.org. It has recommendations for the seismic design of both attached and unattached arrays on flat roofs, and it discusses numerous issues that should be considered for the life-safe performance of these systems, things like clearances, roof slope limits, roof support, minimum interconnection strength of the racking system, firefighter access, wiring issues. It has guidance on friction testing and a prescriptive method for determining the seismic displacement of unattached systems. It has guidance on shake table testing and nonlinear response history analysis, like SunLink has done. SEOC formed a PV systems committee about a year ago consisting of structural engineers, industry, building officials, and other experts. Joe Maffei at R&C was the lead behind this report, and in Joe's work in leading the development of SunLink's seismic design approach was instrumental in producing this document. So we're proud at SunLink that we can play a key role in bringing forward a new seismic design approach that will lead directly to less costly and more roof-friendly, code-compliant PV array designs in seismic areas. I should note there's also a very important technical report just issued on wind design for PV arrays as well. Lastly, I'd like to mention a couple things that are happening on the code development front. In California, the 2013 State Building Code will be issued this coming January, and there's language proposed for this new code from the Department of Housing and Community Development that accepts unattached PV arrays on residential low-slope roofs up to a 1 in 12 slope. There's similar language proposed for the 2015 International Building Code. The California amendments are currently in a public comment period, I think for the next few weeks, and the final action hearing for the IBC amendments happens next month in Portland, Oregon. Well, that's today's webinar presentation. There's more info at sunlink.com. For instance, SunLink has published a couple of white papers covering our wind research program. Those are accessible from our R&D page, and also the seismic videos we showed today are available there. SunLink's R&D findings drive the design of our complete product line, including both our roof and ground mount systems. For our customers, SunLink's research-driven engineering translates into both superior products as well as the ability to support project permitting in virtually every wind, snow, and seismic zone in North America. Visit SunLink's training page for access to our webinar library and information about scheduling in-person training. Additional resources are provided at the bottom corner of this slide. Thanks, everyone. Kate and I would like to now address some of the questions that we received throughout the duration of the presentation. And if you haven't had a chance, we encourage you to use the chat feature to send in more questions that you may have today. After today's webinar, you can also, as noted on the screen, send in questions to webinar@sunlink.com. So the questions so far, maybe Kate, you can answer the question about whether we use static or dynamic coefficient of friction.
In our friction testing, in our full-scale friction testing, we did test at various velocities, and then we ended up using that data in order to sort of capture both what the system was doing as it started sliding and as it began sliding, so both the static and dynamic, and then we incorporated that into our SAP models. And so I have another question here for Rob. Have these results been accepted by DSA?
Well, DSA was very involved in the SEOC document that I just mentioned, published last month. Ron LaPlante at DSA was the chair of that committee that put the paper together, and DSA was an impetus for getting that committee together. So I'm sure they're working on their regulations and incorporating some of the findings that are presented in the new SEOC report. Here's Kate. Maybe you can answer this one. Did you observe a cumulative displacement of the array for the slightly pitched roofs?
So we did, as I talked about, where as long as the system keeps moving, it keeps displacing. So on the pitched roof in particular, when we were at the 4% slope, we did see more displacement than we see on the flat roof because we included our vertical accelerations in our roof motions. And so as the system, as the vertical accelerations hit it, it does jog down the roof a bit. But even on a sloped roof, our overall system displacements were still well within our analysis predictions and very reasonable for what we thought should happen on a roof. So I have one for Rob. What successful approaches has SunLink experienced dealing with AHJs with regard to working around ASC 713.4? And is SunLink available to discuss these issues directly with the AHJ?
Yeah, definitely. We discuss them with AHJs when it's appropriate. And when the questions come up, this unattached approach is currently, as I described, is kind of an alternate method that is acceptable through the provisions of the IBC, but we have to document it to the satisfaction of the AHJ, and that's what we work to do. Now, I see another question maybe related to that. Have I been successful in getting authorities having jurisdiction to buy in using your non-penetrating rack on roofs in California? Yes. It's not, again, the decision is at the AHJ level, but we have numerous systems in California that have been permitted as non-penetrating. Another question concerning rigid conduit with movement of a few inches of array in an earthquake. As you'll find in the SEAC report on seismic design on PV arrays, wiring details have to be considered and designed in a life-safe manner for the array to move. So you'll need some wiring slack or ability for the wiring not to be damaged if that's a concern for life safety.
And there's a question here about whether or not we included large vertical accelerations such as we're seeing in Northridge. And Northridge was one of our roof motions that we fed into the table. So we did both the filtered motion in order to get the range of SDS values, as well as an unfiltered roof motion in order to fully capture that large vertical acceleration. So yes, our earthquake motions did include that.
Again, the question about getting approval from AHJs and SunLink's ability to work with customers, absolutely. That's what Kate and I do when questions arise in permitting a project. We're happy to be involved in that. All right, I think that's it for the questions seem to be coming so far, but if anybody has further questions, again, as you see on the screen, please just send them to webinar@sunlink.com. And I want to thank everybody for listening today and for joining us, and I hope you found it informative. Thank you, everybody. Thank you very much.